Aida Khajavirad. My apologies for any mispronunciation. And Aida is working in, I think, mixed integer programming, linear and nonlinear, which is an area that maybe has had not so much interaction with the SAT community, is my impression. But I think there is lots and lots of room for learning from each other and having interaction both ways. So this is a very exciting seminar to end with. Aida is at Lehigh University, and before that was at Rutgers, University of Texas at Austin, and has also been at IBM, and has a PhD from Carnegie Mellon. But again, the purpose of this talk is not for me to waste time on your CV, but to say warmly welcome. We're extremely happy to have you, and the floor is all yours.
Well, thank you very much, Jacob, for the introduction, and thank you, Ambrose and Jacob, for the invite. As Jacob already said, I'm an optimizer. I have given this talk to the community of nonlinear, mixed integer programmers before, but this is the first time to give it to a more CS theory type community. So because of that, I would really provide as much material, basic material as I think it's proper, but you should feel free to stop me at any point if I say a term which is not clear, or you should, yeah. So I have left a few slides like white in the middle of the slide so that I can use that to write on and explain as needed. All right, so this is a work on binary polynomial optimization, and this is joint work with Alberto Del Pia from University of Wisconsin at Madison. All right, let's start. Okay. So let's start by defining a multilinear polytope. So a multilinear polytope is a set of binary points Z, let me see, yes, such that they satisfy a collection of multilinear equations. So what is a multilinear equation? It's just this expression here, ZE equals product of some ZVs. So let's look at an example right away. So here, for example, I have a multilinear set. So a multilinear set here, you can see that I have a equation Z12 equals Z1 times Z2, Z24 equals Z2 times Z4, Z123 Z1 times Z2 times Z3, Z134, Z1 times Z3 times Z4. And these are binary variables. Okay, and then we let the multilinear polytope to be the convex hull of a multilinear set. In the special case, so you see here, for example, I have a bilinear, the first equation, I have a bilinear term, then I have another bilinear term, here I have trilinears. And I should also say, whenever I say a multilinear term, I refer to a product of some variables. So this is just some terminology here. This is just called a multilinear term. In the special case, when I have a product of two variables, I call that a bilinear term. Okay, so in the special case where all these multilinear terms are bilinear, multilinear polytopes becomes a Boolean quadric polytope. This was introduced first by Padberg in 1989, who is a famous person in integer programming, and later was studied by many other people. This polytope was introduced to study binary quadratic programming, and I will explain more about it. And you can show that this polytope is pretty much equivalent to the cut polytope via a one-to-one transformation, a polytope that is studied in conjunction with the max cut problem. Okay.
Aida, just a question, yes, since we're doing the setup now. So should we also be interested in like linear sums of these Z12s and Z24s?
Yeah, I get to that very quickly, yes.
Okay.
And you will see why.
Sorry
so,
if I get
yes.
ahead. Yeah, but we can
think
of,
worry.
I mean, okay, the like Z123, I can think of that either as a new variable or just as a monomial of degree 3, if I like.
So basically you can think of it, yes, as a new variable, and I will tell you like immediately why I defined this set in the way I did.
Okay, because I'm just you know, engaging in this exercise of making, as we translate between communities, that, you know, I mean, we also have names for these things. We'd set it up probably slightly differently, but just to make sure we're on the same page. But so far, I think we're all good. Okay, good. All right. So why did I define it the way I did? Let's just answer to Jacob's question. Here is a motivation. So I'm looking here at an optimization problem where I'm maximizing a linear combination of a bunch of these multilinear terms, right? So it's a sum, C's are some scalars, positive or negatives, and then I have some multilinear terms here. I'm also allowing for some of these variables to be binary and some of them even to be continuous. Okay, so I claim this is an important optimization problem. So it already subsumes several types of difficult optimization problems. For example, the one that you are probably most familiar is when I don't have any continuous variables. In this case, this is called pseudo-Boolean optimization, unconstrained binary polynomial optimization. And also on the other end of the spectrum, when all the variables are continuous, this is usually called, you know, this problem is maximizing a multilinear function over a box. It is, again, well studied by people, for example, in mixed integer nonlinear programming or global optimization. Okay, so let's say this optimization problem is my starting point. So although I would say a few words that what I'm going to talk about is even more general than this problem, but for now, let's suppose this is the optimization problem that I like to attack. So we know already this problem subsumes several NP-hard problems. Okay, so one common technique in the optimization community is to linearize the objective function by introducing this new variable z. So I introduce a new variable z for each multilinear term, which is again just a product of a bunch of variables. And then I linearize the objective function, as you can see here, and I move these non-linearity, non-convexities all to my feasible set. So now you can see that my feasible set is nothing but the multilinear set. So now I'm dealing with the optimization problem, which is minimizing a linear function over the multilinear set. And also, one thing that I wanted to quickly mention is in non-convex optimization, global optimization, mixed integer nonlinear optimization. So this technique that I said, which has different names like factorable programming, lifting, etc., it's fairly common, and for example, takes the applicability of multilinear sets beyond this multilinear problem that I showed you, but I tell you what I mean by that. So let's say I have an optimization problem of the following. For let's say I'm minimizing z1 square, z2 square, z3 plus z1, z2 minus, let's say, z1 square, z4. And let's say they are even continuous variables. So let's say they are all defined over a box. So when you look at this problem, it's not in the framework that I mentioned, right? Because you don't, this is a polynomial optimization and the variables are continuous, therefore it's not equivalent. So you cannot replace, let's say, z1 square by z1. So what do we do in non-convex optimization? So we, again, in this case, we start by introducing new variables for these nonlinear terms. So I do the following. So I define, let's say, z5 equals z1 square, z6 equals z2 square, and then z7 is now z5, z6, z3, z7 equals z1, z2, and z8 equals z5 times z4. So now you are looking in a space of, well, now 8 variables, and then you can see that now your objective function becomes linear. Now you are minimizing, say, z6 plus z7 minus
Z5, Z4, Z8, subject to these set of constraints, right? So now, of course, the next step would be, well, what do I do with that? Now I tell you a bit, but you already see that even though in the original space, you couldn't see how I could use, how could I see a multilinear set? In this lifted space, you can see that these equations correspond to a multilinear set. So this is to just motivate that understanding the structure of the convex hull of multilinear sets, which again, it's the multilinear polytope, helps us to solve optimization problems beyond those that in the original space even look like what we expect. And this technique that I just described here, this is called factorable programming. Pretty much any general purpose MINLP, which stands for Mixed Integer Nonlinear Programming Solver, relies on this technique.
Can I ask a naive question? Since this
Please.
is a tutorial again, like suppose I'm given a fully Boolean, a 0-1 valued problem, but with multilinear terms. I guess what you showed us on the previous slide shows that by just having these extension variables, I can actually write it as a 0-1 linear problem. And then, so I guess I could then run my favorite integer linear programming algorithm on that. Is that what like is done in practice, or would you do something different or smarter?
So what I showed you in the previous slide is that you do this so you do this lifting, and then the feasible set is the multilinear set.
Yeah.
So now, yes, you can do one step and linearize.
Sorry, I guess my point is that these constraints on Z East, you've written them as multiplications, but it's fairly easy to write them as linear constraints also. Yes. Once we're using the Booleanness, right?
Yes.
So I could think of this as an LP if ILP if I wanted, I guess.
Yes, so this is actually the subject of the rest of the talk. So that is indeed the starting point. The problem is that when you do that linearization, so how do the integer, let's say, MILP solvers solve that? So they have this branch and cut framework, right? So let's say you want to get a bound, lower bound here, you solve the LP relaxation of that problem. Now I'm getting ahead of the talk, but the problem there is, I mean, the answer, the short answer is that the LP relaxation is weak. I think the LP you are thinking about, which is obtained by simple linearization of this product, is weak. So yes, you can indeed input the problem that way, but it will take a while. So the purpose of this talk is to actually give you better LP relaxations.
Ah, exciting.
Yeah, okay. All right. Okay, so yeah, so as Jacob already pointed out, we have this some non-convex problem. So you can think of it, here for simplicity, let's say I'm minimizing a linear function over a non-convex set. Well, it's not really for simplicity, it's as difficult as it can get. But let's say, look at this picture. So what would I do? Well, we all know if we take this non-convex set and replace it by its convex hull, we obtain a convex optimization problem whose optimal value is the same as this non-convex problem. Now, that is not much of a help because constructing that convex hull is fairly difficult. Solving that new convex optimization problem could be fairly difficult because, for example, if the original problem is NP hard, that convex hull doesn't have any politicized representation, etc. So what do we do in, let's say, non-convex optimization? We say, well, the convex hull is difficult to obtain. Let's settle for some convex relaxation of this non-convex set, which is not as tight as the convex hull, but easy to compute and which you can optimize over efficiently. Let's say instead I take this polytope. Okay, so it's obviously a convex relaxation of this set. And now if I minimize over this polytope instead, in this case, let's say I get this point, which is not feasible to the original problem, but I get a lower bound on the optimal value of the original problem. So then the idea is, okay, now if I can come up with some type of iterative scheme such that I can get these tighter and tighter convex relaxations I can put them in some kind of iterative scheme, let's say branch and bound method, and finally I would converge to the optimal value of the original problem. So that's the idea. Now, it's one input, and there are many things that go into this, you know, how would you, so let's say if you are doing minimization, okay, how would I do lower bounds? How would I do upper bounds? What would I branch? All these kind of things would impact the performance of the solver. But here we are interested in the lower bounding step. So the lower bounding step, what we are interested in is to be able to construct these convex relaxations that are cheap to compute. You can optimize over them efficiently, but also the bound that you get are not bad. Okay, so that's really the overall goal in the convexification business. So in this talk, we are interested in the case where this non-convex set is a multilinear set. Okay, so before getting into the convexification part, let me just introduce this hypergraph framework that I'm going to use. So it turned out that there was a lot of interesting material from the hypergraph community, hypergraph theory community, that you could actually use them to study these multilinear sets. So how would I model a multilinear set by a hypergraph? Well, as you may already guess, for each variable ZV, for each independent variable, I define a node. And then corresponding to each multilinear equation, I introduce a hyper edge. So again, let's get back to our previous example. I have Z1 to Z4, that which are my independent variables. So I have 4 nodes here, Z1, 2, 3, 4. So for the first equation, Z12 equals Z1 times Z2, I put this edge 1, 2 here. Then Z2, 4, Z2 times Z4, I put this other edge. For the trilinear, I have this hyper edge, 1, 2, 3. And for the other trilinear, I have this other hyper edge. Okay. And for those of you who, for example, have looked into max cut or binary quadratic programming, you've seen that, you know, this people use graphs to study those problems all the time. And indeed, this hypergraph representation, in case that you're looking at bilinear sets, just simplifies the graph representation that people like Padbury and others have used to study the Boolean quadratic polytope. So here you can see an example there. Okay, so now what do we do with all this? Okay, so so this is like a general practice, again, in non-convex optimization. When you want to study some non-convex set, when you want to study the facial structure of its convex hull, so you start by constructing a basic relaxation, simple one. Let's say, already Jacob mentioned it in the case of multilinear sets. So you look at each individual product, right? So what is the feasible set here is obtained by intersecting all these equations. But now let's take each equation in isolation. And then let's say I look at an equation of the form Z12 equals Z1 times Z2, where Z1 and Z2 are binary. If I just look at this guy as my non-convex set, then we know how to construct the convex hull. Indeed, in this case, the convex hull is given by Z12 less than or equal to Z1, Z12 less than or equal to Z2, Z12 greater than or equal to Z1 plus Z2 minus 1, and Z12 greater than or equal to 0. So this has been known for a long time, and actually it's not difficult to show at all. So similar to this, you can, so this was a bilinear, but you can easily extend this to any product. So let's say if I look at a generic product like here, the convex hull is given by ZE less than or equal to ZV for all V in E, ZE greater than or equal to 0, and ZE greater than or equal to summation ZVV in E plus cardinality E minus 1. So this is, and then also, okay, and also ZV less than or equal to 1 for all V. Okay, so these few linear inequalities give you a convex hull of a set defined by a single multilinear equation over the set of binary points. Okay, and also we know that the convex hull of a intersection of convex hulls is a superset of convex hull of intersections. So if I use that technique to replace each product by its convex hull one at a time, I obtain a convex relaxation of the multilinear set. So this is called the standard linearization. It also has other names, you know, like in the case of bilinears, you may have heard of McCormick inequalities. So people have studied this this polytope in the past. Actually studied it, maybe not so much studied, but used it as a way to construct bounds for, let's say, binary polynomial optimization. Okay, so now I have a convex relaxation as the starting point. So what's next? Well, so one thing you can do is to ask, okay, when is this guy sharp? Are there any conditions under which this guy, this polytope, is indeed the multilinear polytope? And if not, when those conditions are not satisfied, how can I tighten this one? Okay, so this is the question. Now, when we looked at this project initially when I was in IBM, this was only answered, or this was already only studied for bilinear sets. So again, in the bilinear, if all these products are, all multilinear terms are bilinears, multilinear polytope is the Boolean quadric polytope. This has been studied first by Padberg and then by many other peoples. Okay, so one of the first questions Padberg asked was, well, when is the standard linearization sharp? When does it coincide with the Boolean quadric polytope? In the case of again, he was studying binary quadratic programming. And the answer is, well, it is exact if and only if the graph is acyclic. Okay, good. So for example, if I'm looking at a bilinear set, which is of the form Z12 equals Z1, Z2, Z13 equals Z1, Z3, if this is all I have with this graph, then I know what the convex hull is. And it has this very nice compact representation. So this tells you, yeah, if your the underlying graph is a tree, for example, then the problem is polynomially solvable, right? Okay, then what if it's not a tree? Well, what would be the simplest structure that doesn't satisfy that? Well, let's look at a triangle, right? So what happens if my multilinear set is Z12 equals Z1 times Z2, Z13 equals Z1 times Z3, and Z23 equals Z2 times Z3. Okay. So if this is my set, what would be the, let's say, the convex hull in this case? So it turns out that in this case, okay, if I consider the standard linearization, it is not the convex hull. Why? For example, I can look at the point where all of these guys are equal to 1/2. So if I look at the point where Z1 equal to Z2 equal to Z3 equal to Z12 equal to Z13 equal to Z23 equal to 1/2, you can easily check that this half integral point satisfies all the inequalities that are in standard linearization. Now, let's see. So is this the right point? This may not be the right point, but okay. So let me not maybe confuse about this. So the point is the following. So what you do is the following. So if you want to look at, so what you do is you write down all the inequalities that are in the standard linearization. You look at the vertices of the corresponding polytope, and then you see that those vertices are, there are also points that are not 0, 1 valued. Okay, then you try to come up with inequalities that cut them out. So what do I mean? So let's say this is the polytope I'm interested in. And then let's say this is my original relaxation. So what I want to do is to tighten this relaxation. So if you give me a point, like this, which is in the bigger polytope, but then also you can give me an inequality which is valid for the target polytope. Let's say you give me this inequality, and then I can show and I can check that this point is violates this inequality. Then by adding this inequality to my original relaxation, I'm improving it. I'm improving my relaxation. So that's a technique to improve a relaxation. Okay, so in this case, in case of a triangle, you can actually show that you can add what we call triangle inequalities, which are of the form, let's say, for example, z12 plus z13 less than or equal to z1 plus z23, and there are 3 more of them. If you add these triangle inequalities to the standard linearization, then you get a convex hull of a triangle. Okay, so I gave you a family of inequalities. So there are always, the steps are as follows. You need to show that those inequalities are valid for your multilinear set. So they don't cut off any feasible solution to the original non-convex set. So you show they are valid. You also show they cut off some points that are in the weak relaxation. You add them so they improve. And then the next step would be you show conditions under which they give you a new a better representation for the convex hull. Of course, that's not always true. You could come up with these inequalities that improve your relaxations there, and they never give you convex hulls under better conditions. But in this case, what Padberg did was, at first he showed if you have the standard linearization, in case of bilinear sets, it gives you the convex hull if and only if the graph is acyclic. Then he introduced these triangle inequalities. He showed in particular, in this case, they give you the convex hull of a triangle when you add them to the standard linearization. And also he showed more than that. He showed that they indeed, if you add all those, all such inequalities to the standard linearization, you get the convex hull for when G has no K4 minor, or it's called also a series parallel graph. Now, in this case, it's a bit more interesting than just the standard linearization, because the inequalities, actually, I just showed you for a triangle, but actually you can write them for any chordless cycle. And you need to have them for all the chordless cycles in your graph. So in that case, for example, you have exponentially many of them, but you can show that actually you can optimize over them in polynomial time. And this is something I come back later. It has to do with separation versus optimization. I talk about it later. But this was just to tell you like the flavor of the results. So this, for example, tells you, yeah, if now your graph has a certain structure, so now you are allowed to have triangles, you are allowed to have cycles, but now if it's the graph is a series parallel graph, still the corresponding 0-1 quadratic optimization problem can be solved in polynomial time. So now that by itself is interesting from a, just complexity theory point of view. But for optimizers, perhaps there's even a more useful tool that is given here. So when in the process of, let's say, proving that this problem can be solved in polytime, we introduce odd cycle inequalities or triangle inequalities. those guys can be used to improve the lower bounds inside any, let's say, MIP solver or binary polynomial optimization solver. That can be, those guys just, it's true that for general graphs, they are not enough to give you the convex hull, but if you just add them, you can get better bounds. And indeed, and better bounds mean faster convergence for general problems, right? And indeed, for example, these triangle inequalities have shown to be very powerful for general mixed integer quadratically constrained quadratic programs. So there are solvers for those inequalities are implemented there, and they have shown that they expedite the convergence by a lot.
There's a question in the chat, Aida, from Ryan Williams. Can you clarify what you mean by a series parallel graph? There are several definitions in the literature.
Yeah, so this is a graph with no K4 minor, if I'm not mistaken. Yeah.
Okay, thanks.
Yeah. Okay, so yeah, actually, I know I said a lot of things here, but you should ask questions if anything was not clear. Okay, so yeah,
so on that note, I guess I'll take you up on the offer and ask a question then. So like part of why this is relevant is if it happens that your graph is like really, really nice, then now you have something that is theoretically in polynomial time, but
yes,
perhaps equally importantly, you're just saying this sort of indicates that this kind of, if you add some extra constraints, that this could buy you a lot, even if your graph is not on this very particular form.
Indeed. So when you told me, well, I can just do a linearization and give that problem to a MIP solver, what's the problem? Well, if you do that, again, it depends on the MIP solver, but let's say until even a few years, well, actually, I think even right now, if you linearize it and give it as a MIP, I should be careful because I don't know what's going on inside Cplex, but the LP could be pretty weak. But for example, it's just a simple example. If you input it as in the nonlinear way, let's say you put it inside, now Cplex does it too, inside a nonlinear solver, they recognize these multilinear terms, and then they start, even for a general graph, let's say, it's not series parallel. So when they look at the graph, they recognize chordless cycles, they add odd cycle inequalities corresponding to those chordless cycles to the LP, solve that for lower bounding, and then they get better bounds. Yes. So from a perspective of let's say, optimizers who do computational, so if you want to really solve problems to global optimality, and they are difficult problems, this kind of inequalities are very useful because they improve the bounds, and I will show you some numerical results later. And yes, they expedite the convergence by a lot.
And now I'm a bit out of my depth, but I know that people in the theory literature, I mean, on the theory side, and I think people in the audience would be more knowledgeable than me, but on the theory side, we study things like, for instance, like systematic linear programming hierarchies known by names of Shirley-Adams, for instance. That is somehow related to this?
Yes, yes. So yes, that's a very good question. Yeah, so let's say, for example, Shirley-Adams, so they give you a systematic way to get the convex hull of any, yes, let's say 0-1 polynomial program after a certain number of steps. Now the problem is, and steps, I mean just like level 1, 2, 3 different relaxations. The problem is when you get to the convex hull in the extended space, you can have exponentially many variables and constraints, right? Because you introduce many more variables as you go on. The difference between this type of study and that is that whatever we do is in the original space. So I don't know how clear that is, but basically the inequalities are generated in the original space. Now, of course, one method So Shirley-Adams, for example, we use it a lot to, so let's say we come up with these inequalities in the original space, and then we argue if you add it to the standard linearization, you get the convex hull. How can you prove that? Well, there are different ways, but one is to take the Shirley level and relaxation that you know it gives the convex hull. You project out all the extra variables, and then you show that it coincides with your set. So the difference between this and Shirley is that this is in the original space, and because of that, it's computationally feasible.
Okay, thanks a lot.
No problem. Okay. So again, yeah, this was just to motivate you that when we looked at this problem, which is about multilinears of higher degree than 2, there was all this very nice literature on the quadratic case, both in the context of the Boolean quadratic polytope or cut polytope, max cut, all these inequalities, but nothing of a similar flavor for higher degree multilinears. And indeed, if you also looked at the solvers there, well, for quadratic programs, so we are still able to solve, let's say, those problems more efficiently. But we said, okay, let's try to do a similar study for multilinear sets that contain higher degree multilinear terms. And by looking at these results, let's just look at the first one. The standard linearization is the Boolean quadratic polytope if and only if the graph is acyclic. Okay, what would be an equivalent statement or a statement of similar flavor for higher degree multilinear sets? Well, just looking at this result, you would think, well, okay, it makes sense to look at acyclic hypergraphs, right? And that's indeed what we did. Okay, so at least for me, at the time, I was, perhaps not for you, but for me, it was new to read about cycles in hypergraphs. And we found out at the time that unlike the graphs, that there's a unique notion of cycles and acyclicity for hypergraphs. There are different types of cycles, and indeed there are different degrees of acyclicity. So I have listed some of them here. There's Burge acyclicity, gamma acyclicity, beta acyclicity, alpha acyclicity, and probably more. So let me just review some of the concepts that are gonna be useful for this talk. I mean, this is the part that probably you know much more than me, so if you feel like I'm going too slow, just ask me to skip. All right, so what is a Burge cycle? So a Burge cycle of length t, where t can be 2 or more, is a sequence of distinct nodes and edges such that each vi and vi plus 1 is in ei. Okay, so the first thing here you see is that, oh, you can have a Burge cycle of length 2. Here is an example of a Burge cycle of length 2. Why is it a Burge cycle of length 2? Well, here's the cycle. V1, E12, V2, E123, and V1 again. So this is a Burge cycle of length 2. Indeed, you have a Burge cycle of length 2 whenever you have 2 edges that intersect in at least 2 nodes. Okay. And then we say that a hypergraph is Burge acyclic if there are no Burge cycles. Here is an example of a Burge acyclic hypergraph. So you can see it looks very much similar to a tree. So you can just take a tree in a graph, and I mean, it's kind of a fat tree. So once you have a tree, all you can do to, now I want to go from this to that, I can only insert nodes in individual edges. So I can not do, for example, anything at the intersection. You see, intersections here are very easy, have a very simple structure, right? They can only have 1 node. So this is a Burge acyclic hypergraph. Okay, so Burge acyclicity is very restrictive, right? What would be the next type? So we are now going in increasing order of generality. Okay, now we look at gamma acyclic hypergraphs. So a gamma cycle is a Burge cycle of length at least 3. So that's the first thing. I don't have a gamma cycle of length 2. The cycle should have at least length 3, where all the nodes but one in the cycle should belong to exactly two edges. So here is perhaps the simplest gamma cycle you can think of. I have V1, E12, V2, E123, V3, E13, V1. So you can see here, for example, V1 is allowed to be in the intersection of all three edges, but the two other nodes should be in exactly two edges. Now, I claim gamma acyclic hypergraphs are much more general than Birch acyclic ones. For example, in a gamma acyclic hypergraph, you can have Birch cycles of arbitrary length. So here are two examples. These are gamma acyclic, but you can see Birch cycles of length 2 and 3 there. Okay, here is another example of a gamma acyclic hypergraph. Now we can see, for example, in the intersections, I can have more than a node, so it can have a more complex structure, but still a gamma acyclic hypergraph has a very particular property that makes it very attractive to us, and that's the following. Okay, I need to tell you what is a sub-hypergraph. So if I look at, so here is my hypergraph G. Let's take a subset of the nodes. Let's say the nodes that are inside the green edge, I call them V prime. So the sub-hypergraph of G induced by V prime is the hypergraph obtained by intersecting all the edges of the original edge with this guy. So you see, this is the sub-hypergraph induced by V prime here. So you see, for example, here I have a new edge added, right? So a sub-hypergraph can have edges that are not present in the original hypergraph. So I also have now the sub-hypergraph of this guy corresponding to the red edge, to the blue edge. So now let's look at all these guys. They all have a very particular structure. So what that is the following. If I look at any two edges in any of these guys, they are either disjoint or one is a subset of the other, right? So you can see the same thing here and here. So hypergraphs that have this property are called laminar hypergraphs. So later on, when I look at convexifying multilinear polytopes corresponding to gamma acyclic hypergraphs, this is the property that I'm going to use. Okay, so this was about gamma acyclic hypergraphs. Let's go one degree more general. So then the next class is the class of beta acyclic hypergraphs. So a beta cycle is a gamma cycle such that every node in the cycle belongs to exactly two nodes in the graph. So remember in the past, I told you in a gamma cycle, you can have one node that can be present in all the edges of the cycle. But in the case of a beta cycle, every node should be exactly in two edges and no other. So now you can finally think of the usual cycle that we think of. A triangle, for example, is a beta cycle. And we have more examples here. Now, a hypergraph that has no beta cycles, it's called beta acyclic. Now you can see that beta acyclic hypergraphs are much more general than gamma acyclic. I do not have that laminarity anymore. So these beta acyclic hypergraphs have a bunch of other interesting properties, but one thing that I just want you to notice is that if a hypergraph is beta acyclic, then I can always find an edge whose intersection with the rest of a hypergraph is a subset of a single edge, and that such an edge is called a leaf. So a beta acyclic hypergraph always has at least one leaf. So for example, if I look at the triangle, that's not the case, right? If I look at any edge in its intersection with the rest of the graph is not a subset of a single edge. Again, that is the property that I'm gonna use later on. Okay, so this was what I wanted to say about hypergraph acyclicity. These are the things that I'm gonna use later. Are there any questions? Okay, so I'm guessing these parts are probably familiar too. Okay, So now what I'm going to do is the
So
following.
just a question: the hypergraphs that you have on that slide, they're all beta acyclic ones, so no beta cycles.
Oh, so these ones have beta cycles. So these three, they have beta cycles. These are examples of beta cycles. This one is beta
which one?
acyclic
The
hypergraph.
rightmost one. What's the cycle? I guess I'm still parsing the definition.
Okay, so would be V1, 1, 6, 6, 4, 6, 1, 2, 4. Well, I can write it down for you. V1, E1, 6, okay. I think it's clear what I'm writing. E4, 6, then then V4, then E1, 2, 3, 4, and then V1.
Oh, okay.
So if you want to see it very clearly, fix node 2, 3, and 5 to 1, and then you get the triangle.
Mm-hmm.
Yeah. Okay. Yeah. So these are actually examples of hypergraphs with beta cycles. You can find beta cycles here. Yeah, it wasn't clear here. This is an example of a hypergraph that is beta cyclic.
Get it. Thanks.
All right. Okay. So remember, in the Boolean quadric polytope case, standard linearization was the Boolean quadric polytope when the underlying graph was acyclic. So now I want to study multilinear polytopes of acyclic hypergraphs. Okay. To do that, I just defined what it means to be an acyclic hypergraph. Now let's get back to the business of convexification. Okay, so to do convexification, I will do the following. I will use the following technique. Again, this is a bit more general than this study, but not used much. So one thing that is nice, if you can do, is the following. I said if you have a set which is an intersection of a bunch of simpler sets, the convex hull of the intersection is a subset of the intersection of the convex hulls of the individual guys in general. So the two things are not the same. If it happens that by intersecting the simple sets, by taking the convex hull of those simpler sets individually and then intersecting them, you get the intersection of the convex hull, that would be great because that simplifies your life a lot. So what I'm saying is, if I have a set S, which is equal to S1 intersection S2, and suppose S1 and S2 have a rather simple structure, I can always write that the convex hull of S is a subset. I can write that the convex hull of S is a subset of the convex hull of S1 intersected with convex hull of S2. This is always true. Now, when equality holds, that would be a very desirable property. So why? Because then in that case, instead of looking at S, I can just look at S1 and S2, and hopefully they're simpler. So if the equality holds, we say that this set SG is decomposable to SG1 and SG2. Okay, now to tell you, so what I'm gonna do here is I will give you a sufficient condition under which I can say that a multilinear set is decomposable to simpler sets. So once you have that condition, you can first decompose the hypergraph, and then you go and characterize the convex hulls of those simpler subsets. So this is the technique we are gonna use. Now, to give you this sufficient condition, unfortunately, there's a little bit of terminology I should remind you. So I just remind you that, and then we come and I can parse this theorem. Okay, so I already told you what a subhypergraph was. Right, we defined that one already. So there are two other things And again, it's a bit confusing because in case of graphs, it's slightly different. So we also have partial hypergraphs. And then we have also section hypergraph. Okay, so what's a partial hypergraph? So if I have a hypergraph G, V, and E, then G prime is a partial hypergraph of G. So G prime with note state V prime, E prime. If I have V prime a subset of V and E prime a subset of E. So this is a partial hypergraph. Now a section hypergraph is a partial hypergraph where, so if I have G prime equals again V prime, E prime, I have V prime in V, a subset of V, but then E prime should contain all edges in E that are a subset of V prime. So in the graph literature, we don't, okay, well, sub-hypergraph doesn't really make sense in the way that we defined it. Then we have subgraphs and induced subgraphs, right? So subgraph for hypergraph is a partial hypergraph, and then induced subgraph is a section hypergraph, okay? And then sub-hypergraph is something else, okay. So I hope this is not too confusing. Okay, and then one more thing. Given two graphs, G1, V1, this is the last notation, I promise, G2, V2, E2, we defined our union and intersection, as you may imagine. G1 union G2 is just V1 union V2, E1 union E2, and then intersection. Okay, so this is the terminology, but I just realized we hit an hour. Do you want to take a break or? Do you want to do later?
Maybe. So what is this a good time to take a break, or do you want to maybe, you know, state the?
Oh yeah, let me just state the theorem.
Yeah.
Okay, yeah, all right. Okay, so I gave you all the notation. Let me, as Jacob said, let me state the theorem. Okay, so let's say I have a hypergraph G that is the union of G1 and G2. And then I make the following assumptions. The intersection of the two should be already an edge that is present in the hypergraph. And also for, now I will simplify the statement. Let me just read it as is. I know it's not nice. And then for every edge in one of the two, if it intersects with the intersection, it should contain it. Okay, now let me talk about a special case of this, because this is too much. So if I have two hypergraphs, let's say if I have two, so this, for example, says if I have two graphs that intersect in one node, so if this is G1, G2, this decomposes. So for example, if this is my original graph, I can just decompose it to two triangles. So this initially, for example, gives you an easy way of obtaining first Padberg's result. If you have a tree, by this result, it decomposes to a bunch of edges. And then we know that those McCormick inequalities give the convex hull for a simple edge. Okay, but let's make it more interesting. So if two graphs also intersect, if the intersection of two graphs is an edge. So here, let's say G1, G2, the intersection is an edge, they decompose. So this was for some examples for graphs. For a hypergraph, for example, if I want to again think of a special case of this result, if the intersection is a complete hypergraph, then the things decompose. So what that means is if I have, let's say, G1, whatever it is, G2, if they intersect, let's say, if this is my intersection, so it's a complete hypergraph with 3 nodes, it decomposes. So the case where the intersection is a complete hypergraph, that's a special case of this result, but this result is more general than that, and well, it is because what I'm gonna need. So what you only need to remember is, let's say here, my hypergraph, let's say G1 is the blue, G2 is the green. So their intersection is these 3 nodes. So the first assumption says there should be an edge corresponding to those 3 nodes. It already is. Now, this is not a big assumption because if there's no such an edge, as I will do later, I just add it. It's the second assumption that is more important, the one that I've written in blue. So if I look at G1, every edge in G1 that has nodes in G1 that is not in G2 either should contain the red edge, like this one, or should not intersect with it. So for example, I cannot have an edge that looks like this. Now, of course, this is only a sufficient condition. It is possible that what I just draw is decomposable too. And indeed, we don't know necessary and sufficient conditions and decomposability. That very much depends on the structure of the hypergraph. But here I'm giving you one sufficient condition that I'm gonna use for the convex hull characterizations later. So when we come back from the break, I will use this technique to characterize convex hulls for acyclic hypergraphs.
But just to check that, like the top right green edge violates the condition you want, or?
Oh, so this condition is asymmetric. It suffices for one hypergraph to be satisfied.
Oh,
yes.
Ah.
Yes. Yeah.
Oh, thank you.
No problem.
Okay, so I guess, so are you saying that now we should contemplate this theorem for a few minutes while taking a break?
Or just relax a little.
Or, okay, we can, but before, maybe even before doing that, are there any questions from the audience? You can type anything you like in the chat, even more nice even nicer if you just unmute and speak. Any questions up to this point? Comments?
Excuse me, can I? Hi, can I see again the definition of section hypergraph? Because I think I missed. I mean, I don't have all these definitions in my head.
Section hypergraph, yes, it's a partial hypergraph that includes all the edges that are in that are a subset of V prime and R in the original graph. So it's like an induced graph, induced subgraph.
Okay, thank you.
So is it correct that a section hypergraph is a partial hypergraph where you throw in all edges that you possibly can?
Exactly. Yes, you explained it much better.
And then you had this other notion where instead, which was also in some sense induced, but once I fixed my new smaller vertex set, I just took the intersection of all the edges.
Yeah, so in sub-hypergraph, you can have new edges added, right? Because you intersect the original edge set with that smaller vertex set, and that could introduce new edges that are not in the original one.
Okay. As long as they're of size at least 2. So I guess for standard graphs like this induced subgraph thingy and the section hypergraph thingy, they coincide, but in general for larger edges they don't.
Exactly. Yes. Yes.
Okay. Any other questions, comments? Will we take a break?
So when should we be back?
Yeah. So let's take a break and let's be back 15 minutes before the hour.
All right. Sounds good.
Okay. Thank you so much.
See ya.
So it's time to get back to the talk. How are we doing?
Hello.
Hi. Sorry, I lost track of time, I think, just by a minute or two. Any questions before we get started? From anyone? Otherwise, I think we'll just jump straight into it. Again, you can ask questions at any point in the chat. You can also just unmute and speak, as Massimo Lauria successfully did just a few minutes ago. Since I don't see anything, I guess we're just getting started on the second half. Please.
All right. So yeah, we are pretty much done with the background material. So now we can present the results. Okay. So just to recap, the very first question was for a multilinear set, when is the standard linearization sharp? When is it the same as the multilinear polytope? Multilinear polytope is the convex hull. Remember, in case of graphs, Padberg proved that the standard linearization is the Boolean quadric polytope if and only if the underlying graph is acyclic. So our first result is as follows. The standard linearization is the multilinear polytope if and only if G is a Burge acyclic hypergraph. Remember, Burge acyclicity is the most restrictive type of acyclicity. So how would you prove something like this? I just give you a sketch, of course, not much detail. But let's say we first assume that the hypergraph has a birth cycle of length 2. Remember that a birth cycle of length 2 was nothing but two edges intersecting in at least two nodes. So in this case, I use the technique that I discussed before. We first give an inequality which we claim is valid for the multilinear set. Why is it valid? Well, if you look, so again, maybe I draw the associated hypergraph. So it looks like this. I have two edges, E1, E2, that they intersect in at least two nodes. So the inequality sums over all the variables corresponding to nodes that are in E2 but not in E1, plus ZE1 minus ZE2 less than or equal to the cardinality of E2 minus E1. So the only way this can be violated is if everything here is 1 and everything here is 1, right? So if everything here is 1, so I'm saying that all the nodes that are here are 1, right? Then I'm also saying all the nodes that are in E1 should be 1 to make the ZE1 equal to 1. But then in that case, ZE2 is also forced to be 1. Right? So that is just a proof of why this inequality is valid for the multilinear set. Okay, good. So it is valid. The second step is to give a non-binary point, which we have constructed here. We don't need to look at exactly how it looks like, but what is important is that this point is in the standard linearization, but it violates this inequality. Okay, so this by this argument, we conclude that if there is a birth cycle of length 2, then the standard linearization is not the multilinear polytope. And indeed, we gave an inequality to make that point clear. So now you assume that, okay, there is a birth cycle of minimum length, which is at least 3. So I cannot have birth cycles of length 2. That already simplifies things quite a bit, because when you say there is no birth cycle of length 2, you mean that all the intersections of the edges should be at most 1 node. So in that case, if there is a birth cycle of length 3 or so, after fixing some nodes, you will end up, after fixing some nodes to 1 in your hypergraph, you will end up with a chordless cycle. Okay, and the reason you can do that is because we already took care of the birth cycle of length 2 case. So now we can assume that the intersection of all the edges is at most 1 node. So now that I have a chordless cycle, from, from what Padberg did before, I know that in this case, odd cycle inequalities are facet defining and the standard linearization is not the Boolean quadratic polytope. And I can use that to show that in this case, the standard linearization is not the multilinear polytope. Okay, so far I have shown if there is a birth cycle, then the standard linearization is not the multilinear polytope. Okay. Now I go for the converse. So now suppose that I have a Burge acyclic. Okay, just this. Just say I can't talk. Sorry about this. Okay, so now suppose that I have a Burge acyclic hypergraph. I want to show that the standard linearization is the multilinear polytope in this case. So now I will use that decomposition technique. Okay, so the first step is I'm relying on very good memory of you. At some point I told you, if I have a hypergraph which is beta acyclic, there exists always a leaf. A leaf is a edge whose intersection with the rest is a subset of at most another edge. In case of a Burge acyclic hypergraph, which is much more restrictive than beta acyclic, you can show something stronger. If you have a Burge acyclic hypergraph, there is always an edge whose intersection with the rest of the hypergraph is one node. Okay, so again, you can think of a leaf of a tree in graphs. Okay, so now let's take a leaf. Let's call that G1. Let's call the rest of the hypergraph G2. Okay, so the intersection is a node. That is the very, very, very special case of the decomposability result. So I told you if the intersection is a complete hypergraph, it's decomposable. A node is a very special case of a complete hypergraph. So by that decomposability result, I get that the graph decomposes to the green graph and the remaining. Now the remaining itself is still Burge acyclic. So I can use the same argument recursively. I find the leaf, I use the decomposition argument, I keep doing this. At the end, my original hypergraph decomposes to a bunch of hypergraphs, each of which is just a single edge. Well, then I'm done because I know the convex hull of what a single edge is. Exactly, that's what the standard linearization does. So by this argument, I conclude that if the hypergraph is Burge acyclic, the standard linearization is the multilinear polytope. So any questions about this proof? All right then.
So did you need to, I'm just unmuting too slowly, did you need to pick the edges in a certain order, or was it true that in fact like any, I mean, or is it that no two edges can have an intersection of size 2 because that would already be a cycle, or no?
That would be a Burge cycle of length 2, yes. So the hypergraph
I can pick the edges in any order?
So not in any order. The only thing you do know is if a hypergraph is Burge acyclic, there exists a leaf. So we just say, okay, there exists a leaf. Let's take the leaf, right? So indeed, for example, I cannot take this edge as the first one, right? It's
because I want to what's the point? I want to just have I want to decompose into leaves, not into like subgraphs. That's why you're picking off the leaves like one at a time.
Yes, so I want to use the decomposition technique to get a collection of guys, each of which is a single edge. That's what I want to do, because that finishes the proof. Okay. So if you take a leaf each time, you can just detach that single edge. And then on one hand, you will have an edge, which is just as simple as it can be, and the rest remains Burge acyclic, and then I can do it again and again. Okay. Yeah. Yeah, okay. So now this is nice because, well, because the standard linearization has a very simple structure. So, but however, Burge acyclic hypergraphs are super restrictive, as you can see, and I cannot think of any interesting problem whose underlying hypergraph is Burge acyclic. All right, so let's do then something more interesting. So the next step, as we discussed in case of quadratic problems, is to introduce a class of inequalities, valid inequalities for the multilinear set, that we can show they strengthen the standard linearization. We add them to the standard linearization, and then we study conditions under which the new relaxation gives the convex solve. Okay. Okay, so now I define this new class of inequalities. So we call these inequalities running intersection inequalities for the reasons that will become clear shortly. So I will need to define these inequalities. I need to recall what's the running intersection property. Now you guys probably have seen things in different contexts. I kind of found it accidentally, meaning we figured we need this property, and when we were trying to write it down, we found it already there and has a name, which is great. So let's define it first. So a set F of subsets of a set V has the running intersection property if there is an ordering of these guys, let's say P1, P2 up to Pm, such that if I take any Pk in this ordering, the intersection of Pk with all previous elements in this ordering is a subset of a single element. So maybe I can just give you an example right now. Let me look for an example right here. Okay. All right, here it is. So remember, I call those guys PIs. So I use the same. So let's say I have P1, P2, P3. They all intersect in this one node. P4, P5. You know, it's also, I should say, it's a multi-set. It doesn't matter, but you can have identical elements. We need identical elements for later. And then okay, so let's say these, I have P1, so that multiset F consists of these guys, right? PIs, I from 1 to 8. So I claim P1, P2, P3, up to P8 is a running intersection ordering of these guys. Why? So, okay, so if I look at P8, intersected with all the previous elements in this ordering, I will get these, in this case, I will get these two nodes. These two nodes are already a subset of P7. Good. Then if I remove P8, look at P7, intersected with the remaining guys, I get this one node. It is a subset of P6. Good, it satisfies. P6. Now I remove P7. P6. The intersection with the previous guys is the empty set, then that's good. P5, the intersection is P4. P4 is the subset of P4. Good. P4, the intersection with previous is empty. And you can keep doing that to verify this is a running intersection ordering. Therefore, F has a running intersection property. So this is the definition. And based on my very limited understanding of this, this was first discovered in the databases community that they were using this to define acyclic databases. Okay, so why am I using this for? I want to introduce to you a new class of inequalities. So to do that, I say the following. I say, suppose I have an edge, E0, that I call it the center edge. And then I have a collection of edges that intersect with E0 in at least two nodes. And again, that at least two node you already know, because if it's one node, it decomposes, I don't care. So then I intersect E0 with a bunch of edges that have at least two nodes intersection with this guy. And then I assume this is the important assumption that I need. If I look at all these intersections, so the set I'm interested in is just the intersection of the center edge with these guys that I call neighbors. That set should have running intersection property. Okay. If it has it, then I can write an equality that I call running intersection inequality centered at E0 with neighbors EK. I must say there's a lot of notation here, so I really don't want to go through the notation. I just want you to have the big picture that, okay, this was the kind of property I needed. So if I have this property, I can write an equality corresponding to it. And you already see, because of the structure that I assumed, you already can find birth cycles of length 2, gamma cycles, etc. there. So the point is you have a center edge and a bunch of other edges, each of which intersects in at least 2 nodes with this guy. And you need, for the set of intersections, you need the running intersection property. If you have that, you can write this inequality. Okay, so usually for optimizers, I go in detail and talk about how to construct these inequalities, but I don't think how to construct them is much interesting here. I just want to say one thing is you may think the way I can write this inequality depends on the specific ordering I pick. And indeed, there are multiple orders. But when you have a, in fact, you can show if there's running intersection property, there are multiple orderings that you can write. What happens is you can prove that any ordering you pick, if you write all possible running intersection inequalities, then you see that that's independent of the ordering. Okay, so you can pick any ordering. You write down all the possible running intersection inequalities you can do and write for that hypergraph. Turns out that system is independent of the ordering. Okay, good. So in this way, these inequalities kind of have a nice, well-defined definition. Now that I have these inequalities, running intersection inequalities, I define a new relaxation for the multilinear set. So I here call it the running intersection relaxation. This is the polytope obtained by adding to the standard linearization all possible running intersection inequalities. So now we want to understand when this relaxation is tight. When is it the multilinear polytope? Okay, so here actually I don't have a nice if and only if, although now I will switch to a different result that is very clean, but I just want to say this is the most general result we have, that there's a gap here. So what it says is, if the hypergraph is not beta-acyclic, then the running intersection relaxation is not the multilinear polytope. Okay. If it is beta-acyclic, in addition, you need another condition, which again, it's kind of a technical, it's easy to verify. It's something like you cannot have a structure that looks like these 3 edges that more or less look like this. If you don't have that substructure, then the running intersection relaxation is the multilinear polytope. So remember, there's the class of Burge acyclic, gamma acyclic, beta acyclic hypergraphs in increasing order of generality. We already settled Burge. We said the standard linearization is the convex solve for Burge acyclic. Now we introduced a new relaxation. We said not for all the beta acyclic hypergraphs, but for beta acyclic hypergraphs with a specific property, which actually it includes gamma acyclic. So let's say for this class, so which is in between gamma and beta, the running intersection is the multilinear polytope. Is this if and only if? No. So we know if the hypergraph is not beta acyclic, then this guy is not a multilinear polytope. We also know that I can give you an example of a beta acyclic hypergraph for which the running intersection relaxation is not the multilinear polytope. However, this sufficient condition here, I just want to stress it's only a sufficient condition. But at the end, what this tells you is there's a class between gamma and beta for which the running intersection relaxation is the multilinear polytope. Okay, now the proof of this is fairly tedious and technical. You're welcome to look at the paper. So instead of presenting that, I will look at a special case where the result is clean and the proof technique is easier to understand. And that's the class of gamma acyclic hypergraph. So remember, we settled bird, then we presented a result that gives us something beta and gamma. Now I'm gonna focus on gamma and settled gamma. Okay, so it's a special case of this. Okay, so now I'm looking at a special type of running intersection inequalities. So in running intersection inequalities, I was concerned with a case where I had a center edge and a bunch of other neighbors that intersect with the center edge in at least 2 nodes, and they intersect with each other. Now, if I make this extra assumption, which says the neighbors cannot intersect with each other, so this is how the hypergraph would look like, then I get these inequalities that I call flower inequality. Why did I do that? Because in the series of papers we wrote, we first studied these guys and then we generalized them. That's why they have different names. So if the neighboring edges don't intersect with each other, these valid inequalities become much simpler. So we call them flower inequalities. So now I define the flower relaxation to be the polytope obtained by adding all the flower inequalities to the standard linearization. Okay, now we have this clean result which says the flower relaxation is the multilinear polytope if and only if G is gamma acyclic. Okay. So gamma acyclic hypergraphs, we have a necessary and sufficient condition here for their convex corresponding convex hull. Again, what's the idea of the proof? It's kind of similar to Burge acyclic that I said. I just go over it quickly because it also uses the full strength of the decomposition result I showed you. Okay, so let's first do the easier direction. So if there is a gamma cycle, then after fixing some nodes to 1, I will obtain structure which is either a cordless cycle or one of these guys. And then that hypergraph is easy enough that you can tell the flower relaxation is not the convex hull for it. And the way you do it, you just find the valid inequality that is not implied by that relaxation. So this is one direction. The other direction is using the decomposition argument. Okay, so I'm looking at a gamma acyclic hypergraph. I have a leaf. I'm also interested in a maximal leaf. What is a maximal leaf? It's a leaf, so it's at this edge that is not contained in any other edge. Okay, so if I have only, I assume I have at least 2 maximal leaves. If it's 1, it's settled. For now, let's assume I have 2. So let's look at the maximal leaf. So let's call this guy G1, and the rest of the hypergraph G2. I want to use the decomposition argument. So I look at the intersection. In this case, the intersection is already an edge, so I'm good. If it's not, I will add that edge, not a problem. Okay, so the other condition I need to check is every edge in G1 either that has nodes in G1, not in G2, either should include this guy or should be disjoint from it. Why is that satisfied? Because one result that I told you, that a subhypergraph of a gamma acyclic hypergraph is a laminar hypergraph. And indeed, this follows from the definition of laminarity. Okay, so I can do the decomposition. So I get this laminar hypergraph and this other one. So the rest is still gamma acyclic. I go for another maximal edge. You see in this case, now I apply decomposition to these guys. Now this is G1. Now you see that this intersection is not an edge. I introduce a new variable. So I'm going to a lifted space. So I add this edge. I use decomposition. Again, I get another laminar and a new gamma acyclic. I keep doing this. At the end, I'm left with a collection of laminar hypergraphs. So what that means is, if I can characterize the convex hull of a laminar hypergraph, I'm done. Okay. So far we showed after adding at most, let's say, cardinality E edges to a gamma acyclic hypergraph, we can decompose it to a collection of laminar hypergraphs. All right. So what can we do with laminar hypergraphs? So it turns out you can characterize the convex hull of a multilinear of a laminar hypergraph directly. Why is that? So we use here a technique from integer programming, and that is the following. So if I have a polyhedra defined by a system of inequalities, I look at the matrix corresponding to the coefficients of those inequalities. If that matrix is balanced, then the corresponding polyhedra is integral, meaning that the vertices are 0, 1 valued. So you probably would ask me, what is a balanced matrix? So let me just define what that is. So a 0, minus, plus 1 matrix. So the entries could be 0, plus, minus 1 is balanced. So if in every, maybe I don't write it, I just say it. If in every square submatrix with exactly 2 non-zeros per row and per column, the sum of the entries is a multiple of 4. So for example, if you can find a 3 by 3 matrix where the sum of the entries is 6, then this is not a balanced matrix. So starting from the inequality description of a polyhedra, with some extra assumptions that I don't want to bore you with that, if the corresponding constraint matrix is a balanced matrix, then you conclude that that polyhedra is integral, meaning that the vertices are 0, 1 valued. It turns out, luckily, if the hypergraph is laminar, you can show the constraint matrix, the matrix corresponding to these inequalities, is balanced. And therefore, that tells you this is a convex hull description of the laminar hypergraphs. This is the result by Conforti Cornejols about the connection between integral polyhedra and balanced matrices. So here we really were lucky to use this result that enables us to give the convex hull of multilinear, to give a multilinear polytope of laminar hypergraphs directly. Okay, am I done? Almost. The only one, you remember in the process of decomposition, I introduced some new edges as I needed to. So in the last step, you just project them out. So you can, for example, use Fourier-Motzkin, project those extra edges, and then you can show that the flower relaxation is the multilinear polytope. So this is the way we prove it. We first use decomposition, get these laminar hypergraphs. They are very particular. You can characterize their convex hulls directly using this nice result about balanced matrices. At the end, you project out auxiliary variables that you introduced, and we get the statement we needed. So are there any questions about this? Yeah, I know I skipped a lot of details, but you're welcome to ask questions.
Fourier-Motzkin is somehow that you add up the inequalities to cancel out certain variables?
Yes. Yes.
Okay.
So you take a variable one at a time. You look at all the ones with positive coefficient, all with negative coefficient, and you use them to, project out that variable.
Okay, so I think if we're translating this to a SAT setting, I mean, if you're doing this on CNF formulas, I think we would refer to this as Davis-Putnam resolution, but this is something similar, but I guess for integer linear programs, or yeah, for linear programs in general.
Okay.
Okay, great.
All right. So what you just said, but I'm just curious. So because this is only applicable to linear systems, is that more general?
This is just an observation that if you do exactly like if you write a CNF formula, a formula in conjunctive normal form, I mean,
Okay.
you can just write it as a sum of the literals greater or equal 1, right? And now as a 0-1 linear integer linear program, that's just the same as the original CNF formula. And now it's just the fact that if you systematically one variable at a time just add up all constraints with the variable appearing positive and negative to cancel them out, and you do this variable by variable, then you'll derive 0 greater or equal 1 if and only if the CNF formula was in fact insatisfiable or not.
Yeah, so yeah, that is also indeed to show if a system of linear inequalities is feasible or not. Of course, it is kind of theoretical, but yeah. So in this case, you know, it's messy, but you can use it to prove this. In general, it's obviously it's like double exponential, so you don't do it.
Yeah, no, it's not a good idea for SAT solving either, but it's my understanding is it's fairly powerful as a pre-processing technique, as a pre-solving technique in some limited settings, but you wouldn't use it as a general method.
Okay. Okay, so now let me say a bit about, so I gave you this polytope, the flow relaxation polytope or the running intersection polytope, and I told you when are they the convex hull. But how efficiently can you solve over them? So actually, if you look at the, even the flower one, if you look at the definition, it tells you take a center edge and take any subset of the neighbors that they don't, such that they don't intersect with each other, and then you can write an inequality. Now you can think that if I have a center edge and then let's say m other edges that are neighbors, I can write of the order 2 to the m flower inequalities. And indeed, you can come up with an example where all of these guys are facet defining, meaning that none of the inequalities are redundant. They are indeed needed to characterize the convex hull. So that tells you this polytope in general could have exponentially many facets. However, what you can show is that you can solve over it in polynomial time if the hypergraph is gamma acyclic. So what do I mean? So maybe you guys are familiar with this, but in case you are not, about separation, I just tell you what do I mean when I say separation. So in this case, let's say I have a hypergraph G, so G is given, and a family of valid inequalities for the multilinear set. So let's say in this case, flower inequalities, running intersection inequalities. So the question is the following. Okay, and I am also given a point, z bar. Let's say it's in the unit hypergraph. So the question is whether this point satisfies all those inequalities. If not, give me an inequality from that family that is violated by this point. Okay, so this is the separation problem. So it's defined for over a family of inequalities. You give a point. Does it satisfy them? If not, give me an inequality that is violated by it. So what you can show is that if the separation problem can be solved in polynomial time, then the corresponding optimization problem, which is the problem of minimizing a linear function over those valid inequalities, can also be done in linear time. Okay, in polynomial time. Okay, so the two things are kind of equivalent. So for what we can show is the following. So we can show that if you have a gamma acyclic hypergraph, you can separate over flower inequalities in polynomial time. even though the flow relaxation itself has exponentially many facets. So that implies optimization problem over gamma acyclic hypergraphs is polynomial. Now, what happens is separating flower inequalities over general hypergraphs, though, is NP hard. So why is that important? Remember, when I motivate these things, I was saying, well, these results give you polytime solvable cases, but what you also like is to use those inequalities to improve the bounds for general classes of problems. So so far we said, if your underlying hypergraph is gamma acyclic, you are in luck. Even though you have exponentially many inequalities, you can solve the separation problem over polytime. The optimization problem is polytime. However, if you have a general problem and you want to use the flower inequalities to improve it, the separation problem is NP hard. So that's at the beginning, it's kind of it's negative. However, what is the thing that goes into the exponent and gets things bad is the rank of the hypergraph. So what is the problem input? Maybe I should have said that. It's, so you get your hypergraph is your input, and you want to see whether it's polynomial in V, E, and the rank of the hypergraph. Now, what is happening is the rank is causing all the trouble. So I will make the following assumption. I will say, well, and what is happening is if the rank is fixed, then the separation problem is actually easy. You can do it in polytime. Now, I would claim this is not a bad assumption. Why? Because in polynomial optimization problems, well, V is like the number of variables. E is the number of multilinear terms. They can be very big. You can have thousands of them. But then R, the rank of the hypergraph, is just the degree of the polynomial optimization problem. And oftentimes, almost always, that is much smaller. And indeed, if you go to higher degrees, let's say if it's more than 10, and if you want to solve that problem, even like numerically, the round of errors will kill you. It's not even doesn't get to this point. So here we are going to assume the rank is fixed. Once you assume the rank is fixed, then the separation problem, not only over flower inequalities, but also over the most general class, which is the running intersection inequalities, can be solved in polytime. So what we do is, we devise some separation algorithm based on a variety of heuristics and ideas to just solve it efficiently. Okay, so I show you some numerics, but this would be the time if you have any questions about anything theoretical so far.
I'm a little bit curious how dependent these characterization results are to which kind of linearization you perform. Like, I don't know if you can see in the chat, it's kind of hard to read out the math, but there are like if I want to say that if I have a monomial of degree 4, and I want some variable that encodes that all of these 4 variables are true, then I guess I could write like 4 constraints saying that if my new variable z is true, then this forces x1 to true, and then another similar constraint for x2 and x3 and x4. Or I could just write them as I think this is called a big M constraints, like minus 4z plus all of the x's greater or equal 0. And the question is, like, if you start playing around with aspects like this, would this affect these results like in a major way, or would it be more of a technical nuisance, but the end result would be kind of the same?
So if I understand your question correctly, in the things that I discussed, there was, so big M is, it's a different story. And as you said, the way you linearize will change the quality of the relaxation. Okay. Here, there's not such ambiguity, though. So I gave you exactly what is the relaxation, right? So given this linearization, this is the result. So
and I guess so I'm trying to change the linearization.
Oh yeah, for sure, it will change the
Okay, it will be like, then it's like, oh, then we have to start over from the beginning and see if
so yeah,
something...
you are looking at a different polytope potentially, right?
Yeah. Okay.
Yeah.
Which also, I guess, raises the question of like that you could potentially play around with all kinds of different linearizations and see if...
So I think one thing that you may want to say is the way you write your multilinear function is important, because you know how like there are multiple ways of writing, right? Like in a, like they call posi form. I'm trying to remember the things that like in pseudo-Boolean optimization, you can like write, you know, as the sum of some 1 minus some you let x, some 1 minus x. There's not a, so given a bunch of binary variables, you can binary points, 0.1 points, there are different ways of fitting them to a multilinear function, right?
Yeah.
So yes, the way you choose, there are sums that are better than others, because based on how you choose what that exact multilinear function is, the hypergraph will change. And finding the best way to write that is a difficult problem. I don't know how much you followed, but it's like based on which variable to switch and which not. Okay.
But I guess the reason the standard linearization is called standard is that you guys like it.
Oh, well, the reason it's called standard, well, it was called standard like 4 years ago by a guy, and they followed. But what I wanted to say was that's after the step I said, because I'm already assuming at this point I have sum of a bunch of multilinear terms. What I was trying to say was the following. You can first switch some variables. So let's say replace x by 1 minus x, some of them, and then call them new variables, and then have it in the multilinear form I have. So that extra pre-processing changes the problem.
Okay.
So, for example, you know, the thing that, well, if I have a multilinear functions, sum of products, if all linear combination of products, let's say I'm maximizing, if those coefficients are all non-negative, then this is a supermodular function and the problem is easy. Now, you can give me a multilinear function, then it's fully expanded form. It's not supermodular, but then by switching a subset of variables, you can get a supermodular function. And if I believe that problem is NP hard. So that's what I was saying. It's, you know, the way you write that expression, what variable to switch versus what not to, that changes the hypergraph, that changes the difficulty of the problem. But once you settle that, okay, once you settle on the multilinear set, once you tell me this is the multilinear set that I have a hypergraph for, then the complexity of this linearization is not a function of really how to choose things. It's fixed at that point.
I see. Okay, thanks.
No problem. Okay, so maybe let me show you some numerics. So this, I show you two. The first is here we just generated a collection of random optimization problems. There are polynomial optimization problems of degree 3 and 4. Variables are even continuous. So you do one level of, so like whenever you have x1 square, you introduce it by, replace it by a new variable, and then in a lifted space, you see that those multilinear sets. We consider different number of variables, different sparsity patterns, and then different number of constraints. So actually, I should say it's not even unconstrained polynomial optimization. You also have inequalities that are polynomials, okay? Now, what we do is, for each combination, we generate a bunch of random instances. So we are doing the following. So we want to solve these problems to global optimality. There are a bunch of solvers out there for mixed integer nonlinear problems. So we want to measure, or we want to show the impact of the inequalities that I told you in expediting the convergence rate of this solver for general problems, the problems that they don't have any kind of a cyclicity. You see, it's even like you have constraints, things are continuous. So you just want to use those inequalities at cutting planes inside the branch and bound approach. So here we are using one of those solvers that is called Baron, Branch and Reduce Optimization Navigator. It is a commercial solver. It's available under, I'd say, GAMS, Ample, MATLAB, so you can use it. It's also available for free on NEOS. Here we used it under GAMS. So we are just measuring. So we solve, given a polynomial optimization problem, I solve it under two settings: barren default, and then barren with the cuts, running intersection cuts added to it. And these cuts are included in every node in the branch and bound tree. You solve a cheap relaxation, then you get the solution, you solve the separation problem over that point, meaning that, does this point satisfy the running intersection inequalities? No. If not, give me some that violates it. You add it to the relaxation, you solve it again. So here I'm measuring the impact with respect to the CPU time, number of nodes in the branch and bound tree, and memory requirements. So you can see with cuts on the horizontal axis and without cuts on the vertical axis. And you get like 50% reduction in CPU time, which is pretty good because the solver is already very well developed. So there are a ton of things going on there. So this is for polynomial optimization problems of degree 3. Here's a study for degree 4. You see similar improvements. This is pretty much, these are the measures that we are hoping to see improvement for when we work on these kind of solvers. And then finally, here's an application. This is a problem in computer vision. It's called image restoration. So you have a blurred image and you want to understand what was the original image. That can be written as an unconstrained polynomial optimization of degree 4. So unconstrained 0, 1 polynomial optimization of degree 4. If you look at the hypergraph of these guys, they are not even beta cyclic. So they have beta cycles. If you put the running intersection cuts in barren, you can see that the improvement is even more than the random problems. You can see more than 60% CPU time reduction. And again, this is just to show you, even though in this case, these inequalities are not enough to characterize the convex hull, adding them to the relaxation leads to better bounds. Better bounds mean faster convergence in general. And indeed, this is the case here. So let's see. Okay, that's pretty much it. And here are a number of papers that we wrote over the years. If you are interested about the details, you can take a look. And of course, if you have any questions, you can always email me. Thank you.
Thanks a lot, Aida. I'm doing the the collective round of applause for everybody on Zoom. This was great. Again, it's a great opportunity for us to learn a little bit about what's going on the other side over in mixed integer linear and nonlinear optimization. Again, I think there's a lot of room for more communication between this community and the SAT community, and I'm very happy that we had this seminar. I could certainly think of a bunch of questions, but this you've already heard, so I should maybe give the opportunity to others to ask their questions first. So, or if people are thinking, so one thing that I'm curious about is, so I guess this is something that works well for inequalities. If I had equalities, is there any comparison on these kind of methods, or just throwing like a Gröbner basis solver at it?
So by inequalities, you mean in the original set, or so?
Yeah, suppose that my original problem was a set of equalities. Then there's sort of just multilinear polynomials, and I was just curious whether, I guess I could feed such a problem either to like Barron or something similar,
yeah,
or
yes, you can.
Or I could try to pick a good Gröbner basis solver from the computational algebra people and see how that does. Is that like, do you ever compare against such?
I have not. In case of mixed integer nonlinear programming solvers, as long as you can write it as a problem of maximizing, minimizing an objective function subject to a bunch of constraints, equality, inequality, so you have an algebraic description, you can input it to Baron. Now, of course, that doesn't mean that, because it's basically the proof of these algorithms that will at some point converge. So how fast it converges, it's really depends on the very specific structure of the problem. And unfortunately, it's also very a function of how you exactly input the problem. Because as you can see, this convexification, like that recursive technique that I told you, how to introduce new variables and, you know, get this, that very much. So you can take the same problem and just write it in, like, factor something out and then write it down. The quality, the solver may become much slower or faster. So just the short answer is I haven't done the comparison, but you can input certainly those problems in. Unfortunately, these solvers are general. Unfortunately, they still require a lot of user expertise. So you should kind of, I mean, they are getting better, but it's not like convex optimization. So you should know a little bit about how they work to make sure that you use them to their full potential.
I see, makes sense.
Oh yeah, so if you ever want to use Baron, I should do a little bit of maybe advertisement, because the owner of Baron is my former PhD advisor, and I worked on it for quite a few years. I'm not actively working on it anymore, but in case you have any question about how to using it, you can always email me.
And how does this compare to, I mean, to what extent are these capabilities that also, I guess when you start talking about MIP solving, you know, the people drop names like Cyclic, Groby, Express.
So well, I think it's, well, I don't know what Ambrose would say, but I say Baron is the state of the art. There are a few others. Well, yeah, I let Ambrose do. I'm biased, so I'm in the Baron team.
And are Skip and Baron friends, or like mortal enemies, or somewhere?
Oh no, they're friends. Skip actually is great. Skip is open source. Baron is not open source. I should say that. It's commercial.
I think that Skip and Baron have a bit different strengths. I mean, Baron, like for very nonlinear problems, is definitely the state of the art and outperforms Skip, I would say, especially if you don't have integer variables. If you have like a large MIP component, then I could imagine that sometimes Skip still can outperform Baron. But I mean, this depends on the application.
Yeah. So you could, you know, at this point, you could just give all of them a try and hope for luck, you know, because these problems are at the end difficult problems. So, you know, when people like, oh, you do non-convex optimization, I have this problem with a few thousand variables, and to them a few thousand is nothing. I'm like, yeah, sorry.
Okay, so you're saying like the nonlinear problems, they get hard pretty quickly.
Yes, but also there is no, I mean, for example, how you measure difficulty, it's not very clear. So it's not just the scale. It really depends on the type of non-convexity. But yeah, I mean, I must say again, because, you know, I worked on Baron when I was a student. That was a long time ago. I worked a bit after. Now I'm not so involved into computations. So I might be very outdated. But the times I was involved in it, yeah, as Ambrose said, Baron's strength was a lot into non-convex nonlinear problems. From what I know, there has been a lot of new development in the MIP part of it now, but I really don't know how it compares with Skip. But another new and upcoming solver in this space is Gorubi. So I heard people talk about that a lot, especially for mixed integer quadratic problems. And there are like a group of new people working on it. So that could be also a potential competitor for future.
Here's a final high-level question to you, Aida, maybe also to Ambros. Like from the MIP side of things, is there any like interest in or outreach to other communities like constraint programming, or I don't know, satisfiability modulo theories or something, like anything that you see there that like this is cool, this would like to import, or is it like, or in general, any thoughts about like potential for interaction, or maybe not so much, like you have your techniques and they work for the problems you need to solve?
So in Barren, it's called branch and reduce because at least when it was developed, there's a lot of constraint programming going on inside. And so one thing that I didn't talk at all about is, so when you construct these lower bounds, the tighter the bounds on variables, the smaller the domain, the better the quality. So they do a lot of techniques from constraint programming as pre-processing to, you know, filter the domain, like the things that you guys say. So some of those things are already there. The only person I know who is actively working at the intersection is John Hooker at Tepper, who does constraint programming and optimization both. Yeah, I don't know, Ambros, are we trying to reaching out to the constraint programmers?
I think not hugely as a community, I would say, but individual people do.
I think there's a lot of constraint programming in Skip too, right?
Yes, I mean, the conflict analysis is something that's definitely inspired by SAT and pseudo Boolean solving. And I think that's still not the end of what is possible.
Yeah. Yeah.
Yeah, so I think I'm looking if there are any final questions in the chat, but we already, I mean, we should let you off the hook. You've been talking to us for quite some time now. Just I put a reminder in the chat that all registered workshop participants are welcome to meet at GatherTown. And I guess we, with that, I think we can conclude today's seminar. So Aida, again, thank you so much, and thank you
so much for having me. Thank you very much.
Thank you.
Have a nice day. Bye-bye.
Thank you very much.